We've looked at separable first order differential equations. What we're going to look at here is what happens if we're unable to get them in the form where we can separate it, so everything dependent upon an x on one side and everything dependent upon a y is on the other. So we're going to look at standard first order differential equations and our approach to solving these, because it's not quite as simple as just put one thing on one side, one thing on the other, and integrate both sides. We have to use a special technique and introduce a new concept called an integrating factor. Now, first order differential equations can be expressed in this form. So dy by dx plus p of x times y equals q of x. Now p of x, q of x are just generic functions of x in whatever format we want. The y is kept as the y, and then you've got dy by dx here, indicating your derivative of y with respect to x. Now we want to be able to solve this type of equation. Now in order to do that, what we're going to do is we're actually going to start by considering the derivative d by dx of I of x, so some function in terms of x, times y. Now we know that if y has a dependence upon x, what this means is that can be written as I of x dy by dx plus I dashed of x, so derivative of I, times y. So what this allows me to say is fine. So conversely, I can integrate both sides and then say that the integral of I of x dy by dx plus I dashed x times y, all with respect to x dx, has to equal I of x times y. Yeah, we're just going back on what we've said there, and we realise that we can turn it round and express it the other way. Now, this side here, if we can look at the left-hand side, let's call this original equation equation 1. If we can take this left-hand side here and express it in a format that looks similar to this, what we're then able to do is simply write out the integral by multiplying through by a set equation and making it look in that format there. So let's imagine we're going to take this equation, equation 1, and what we're going to do is take I of x, so this function here, and we're going to multiply it through this equation here. What we'll then end up getting is we'll end up getting I of x dy by dx plus I of x times p of x times y equals I of x times q of x. So we've added that element into our original equation and been able to rewrite it in this format. Now what I'm going to do is I'm going to take these equations, so I'm going to take this one here, let's label this one as equation 2, and this one here is equation 3, and what I'm going to do is I'm going to compare the coefficients of y in both of those. So if I compare the coefficients of y here and the coefficient of y here, what I'm able to then say is that I of x times p of x is equal to I dashed of x. What that then means is I can rewrite it and say that p of x is equal to I dashed x over I of x. Now if I were to integrate both sides here with respect to x, so make it the integral of p of x dx equal to the integral of I dashed x over I of x dx, well this one here on the right hand side has a standard format of being a logarithm. So that equals ln of I of x. And what I'm going to do here is I'm just going to ignore the plus c in this one because I'm equating these two equations. And that then allows me to rewrite that I of x and state that fine, using this and taking the ln across, taking my logarithm across, I can say that I of x is equal to e to the integral of p of x dx. Now I mentioned earlier we were going to introduce a new concept called an integrating factor. Well, that is this element here. This is our integrating factor, and what we have to do is introduce this in order to be able to solve it and get our solution to that original differential equation. Now, if we take this original differential equation and multiply through by this integrating factor here, what I'm then able to say is that I'm going to get it in the format of this here, such that I can simply write down the standard integral of the left-hand side, to then compare it with the right-hand side, integrate whatever's on that side on its own, and get a solution to this differential equation. Sounds a lot more complex than it is, but actually it's one of those techniques that's easily seen and done when I show you a couple of examples. There's just a couple of set steps you have to remember whenever you do a question like this. The first thing you always have to do is arrange it in the correct format. So we have to have it written in the form dy by dx plus p of xy equals q of x. Key thing to remember here is the coefficient of dy by dx is unity, i.e. 1. So we always have to have the dy by dx on its own. What we then want to do is calculate the integrating factor, which, as we've just stated before, is e to the integral of p of x dx. So it's e to the integral of whatever this value here is with respect to x. What we then do is multiply through by the integrating factor to get an equation of the form d by dx of ixy equals f of x. Now this f of x on this side will be the equivalent of the q of x times the integrating factor. So we have to bear that in mind as both sides have been multiplied by it. So this will be given by something of the format q of x, whatever was there before, times my integrating factor. We then integrate both sides and simplify when possible, and that will give us a general solution. Then, if limits are available, we can substitute them in there to get rid of c, or if we've got an initial condition, we can do the same sort of thing. So it's several steps, 5 steps there that we have to follow, and if we do follow them, we'll get a solution out every single time. Let me show you how to do this in a couple of examples. So let's imagine I ask you to solve the differential equation dy by dx equals negative 2xy equals 3. Now, the first step is we have to make sure it's written in the correct format, dy by dx plus p of xy equals q of x. Well, this is in that format because there's no coefficient in here, dy by dx, except 1. What we now have to do is calculate the integrating factor, I of x. Now we know I of x is equal to e to the integral of p of x dx. Now remember, the p of x comes from the coefficient of y. Now one key thing here is it has a negative there, so the negative goes with it. Remember, it's dy by dx plus p of x times y. So in this case, my p of x equals negative 2x. So my integrating factor becomes e to the negative integral of 2x dx, which is equal to e to the negative x squared. Now a point to note here, normally when we do an integral there's a plus c. We don't have to worry about the plus c in this case. For the integrating factor, take your plus c as being equal to 0. We don't have to take that element with us into the original equation. What I'm then able to do is multiply through by the integrating factor, and I can write that fine, so d by dx we know is going to equal I of x times y, so it's going to equal e to the negative x squared times y, and that's going to equal 3x, but it's then going to be multiplied by the integrating factor, which is your e to the negative x squared. What we can then do is integrate both sides with respect to x, and I can say that y times e to the negative x squared equals the integral of 3x e to the negative x squared dx. So it's now just a case of integrating that right hand side using any of the techniques that we've covered up to this point. And if I were to do that, I'd end up with y times e to the negative x squared equals negative 3 over 2 e to the negative x squared plus a constant of integration c. We then divide through by the e to the negative x squared, so I get y equals, I'll end up with y equals negative 3 over 2 plus c over e to the negative x squared, which can be rewritten as negative 3 over 2 plus c e to the x squared. So there you go, I've got my solution to that one there. Now this here has two parts to it. This here is what's called a particular solution. So y equals negative 3 over 2. That's what's called a particular solution because it is a set solution for that family of equations if I were to be given something for y and x. This one here is what's called the complementary function. Now this complementary function, y equals c e to the power of x squared, that's the one, because I've got a dependence upon c, that changes it and gives me an entire family of functions which can then be used in here. If I were to have some initial conditions, then I could substitute them in at this point to eliminate that c and calculate it, such that I could have one specific answer for that set of solutions for y and x. Second differential equation I'm going to solve here is x dy by dx plus 2y equals x squared. So step one was to write it in the correct format. Now I've got a coefficient here of x in front of the dy by dx. So what I'm going to do is I need to get rid of that. So to get rid of that, I'm going to take the entire equation and I'm going to divide every term by x. So what that means is I can rewrite it as dy by dx plus 2 over x times y equals x squared divided by x equals x. I can then calculate my integrating factor, I of x. I know that is going to be equal to e to the integral of p of x dx, which is equal to e to the integral of 2 over x dx. Now integral of 2 over x dx, that's the equivalent of 2 times the integral of 1 over x. So that's the equivalent of e to the power of 2 ln x. That's e to the ln of x squared, which means my integrating factor is simply x squared. So what I can now do is multiply through by this and get my two sides. So I can say, fine, so that means my original derivative d by dx of x squared times y, that gives me what was an x on this side times this x squared gives me x cubed. So if I integrate both sides, I can say that x squared times y equals the integral of x cubed dx, which is equal to a quarter times x to the power of 4 plus my c, my constant of integration. If I then divide through by x squared, I get y equals 1 quarter x squared plus c over x squared there. So there you go, that's me got my solution to that equation there. At this point, as I've mentioned before, if I had initial conditions, I could substitute them in to find that c, but in this case, I don't have to worry about it. I've got my solution there. Now again, a point to note in this one is that I've got a particular solution and I've got my complementary function. Particular solution here is this one, my 1 over 4x squared, so that satisfies the original equation. This one here, the c over x squared, arbitrary constant c, gives me a family of solutions to satisfy the differential equation. So it expands it beyond that one simple solution that's there. Whenever we solve a differential equation, solve a first order linear differential equation, this is the kind of solution we'll get. A general solution in terms of a family of functions. Initial conditions will help us whittle it down to a set solution for that family if we have them available to us. You just have to remember the steps, so those 5 steps that we need to do in order to be able to get this solution and be able to make it work for us in the context of the question we've got.